Our next speaker is our co-chair for the meeting, Professor Alex Ellerly from Carleton University. Alex is a Canada Research Chair, as I mentioned last night, a very prestigious, about as prestigious a position as you can occupy as a Canadian professor. He's written 2 textbooks on space robotics and is now working on a popular science book with the intriguing title, Manna from Heaven, How to Save the World. His interests are in space, planetary robotics, robotic astrobiology, in situ resource utilization, planetary industrialization, biomimetics, and self-replicating machines.
Okay, thank you very much. I'm going to be talking about something which is probably not talked about too much in the interstellar community, and that's artificial intelligence. But first, I'm going to introduce the artificial intelligence by way of robotics. So first of all, I'm not going to discuss things like human interstellar flight. I'm really only going to consider robotic missions. Obviously, interstellar flight will require autonomous operations. For the most part, even if humans were on board, they'd probably spend most of the time asleep anyway. There are several approaches to what I'll introduce in a few minutes, is the concept of availability. Now, if you take the Lubin approach, which basically imposes extreme redundancy, a kind of scattershot approach with minimal cost per nano spacecraft to permit millions of these devices to be sent off into interstellar space. Now, this makes a lot of sense for today, but I want to actually look at a slightly different approach, which is a more targeted approach. Most of you are familiar with the sort of like the Daedalus concept, which was some kind of nuclear propulsion system. But what I talk about today is also applicable to laser-propelled starships, such as the Bob Forward type of approach. So let's look at let's classify interstellar missions. There are 3 types. We've got the Flyby. Breakthrough Starshot is one of those, and in fact, the British Interplanetary Society Daedalus was also a flyby. The second type of mission is where we want to essentially decelerate at the target system and to perform in situ exploration of the extrasolar system, nominally to search for life or whatever. And again, Bob Forward's architecture introduced this kind of concept. One of the things that, for reasons I won't go into now, is that one of the techniques that I particularly favor is the free electron laser, which if I come back to it, I will explain why that's the case. And of course, there's the third approach, the third type of mission, which involves some kind of encounter. And there are 2 types of possible encounters. One is some kind of encounter with some kind of biological extraterrestrial intelligence, and the second one is some kind of encounter with some kind of artificial extraterrestrial intelligence. And they would both involve 2 slightly different approaches, but I don't want to talk about that today. What I want to talk about is the transit phase. All of these types of missions involve some kind of transit phase lasting particularly 50 to 100 years or so. So with that, I assume that the interstellar spacecraft basically has to encapsulate a significant amount of engineering investment with extensive payload instrumentation, i.e. high cost, some kind of Daedalus type starship, no matter what the propulsion system might be. Okay, so let's look at some potential dangers that may occur. I assume, obviously, the Kuiper Belt and Oort cloud icy bodies are fairly diffusely distributed and do not represent particularly important collision hazards. We can deal with things like high particle flux from the interstellar medium, can be mitigated through eroding some kind of shielding. The radiation environment, dominated by high-energy galactic cosmic rays, one of the assumptions I'll make is that onboard electronics is based on vacuum tube technology. There's also another potential danger which I want to address a bit more seriously, and that's random stuff. Any kind of long-duration component exhibits a bathtub failure rate, just the distribution over time. So you start off with a high level of infant mortality, and then that drops to like a background rate, but with effectively a sort of roughly constant probability of failure rate, and then that again increases towards its end of life as the senility issue arises. All spacecraft can fail. Spacecraft do fail. They fail quite frequently, actually. Now, most approaches these days with satellites is to basically upload software workarounds. And these essentially reconfigure the mission. And the example I give in my lectures is Exosat, which basically had a failure. And through its mission lifetime, these failures propagated and increased in complexity as the mission proceeded. Hardware failures obviously require redundant systems. And an example of that is the Galileo Jupiter mission, where the main antenna failed to open effectively. Now, it actually possessed a low-gain antenna as well. So by uploading some compression software, it was enabled to recover that mission and get about 70% of its data back. There also exists currently quite a few modern fault diagnosis methods based on things like the Kalman filter, principal components analysis, and neurofuzzy systems as well. So the 50 to 100-year starship concept, interstellar transit, introduces the problem of availability. Now, the 100-year starship study advocated multiple redundancy, high reliability components, and a technique called evolutionary hardware. Now, evolutionary hardware was based on field programmable gate arrays, which could then be essentially reconfigured using genetic algorithms. So if we look at availability, there are actually diminishing returns to redundancy. So if you look at the formula there, it's very simple. We have a ratio between the mean time between failure to a series of three other parameters. Now, the current traditional approach to increasing the availability of a spacecraft is to increase the reliability of the individual components. But there's a limit to that. There's no component can last, we have no experience of actually building components that last 100 years, for example. There are other approaches as well to increase the availability, and that is mean time to repair, which is a measure of maintainability. And for this, we'd need some kind of onboard servicing. And then there's mean time for supply, which actually is a logistic measure, which implies that we would need some kind of onboard manufacture. So to get the highest availability for our interstellar flight, we will need to have all these elements in place. And in fact, the Daedalus starship was supported by several of these wardens. These were kind of free-flying robots, similar to current free-flying servicer concepts being floated around, with arms to basically fix essentially the exterior of the spacecraft. And given that we have been doing a lot of servicing missions over the years, there are certain lessons from space servicing. And the first and most important one is that we need to have some kind of standards of interfacing between modules to ease the kind of robotic complexity we need for changing out systems. The other thing, of course, is that any kind of robotic handling is going to be very challenging. Now, modularity imposes the simplicity of robotic handling, and it assumes that there's a kind of a stockroom of pre-manufactured modules for replacement. Now, this isn't very realistic for a starship. So in order to implement full availability, the starship, in my opinion, has to be designed for self-repair. So we need to have some kind of self-manufacturing facility on board to replace any component on demand from a limited feedstock. So even though we're talking about a relatively structured environment, onboard manufacturing will require a certain degree of onboard intelligence. We need to plan manufacturing schedules. We need to implement conflict resolution. We need to employ Bayesian interpretation of data in relation to hypotheses, pattern recognition, and so on. So the level of intelligence required to implement these capabilities will be relatively significant. Now, it's crucial to minimize the range and amount of feedstock we require to maintain and repair the Starship. So this introduces our Demandite concept, which essentially matches functional material requirements into a fixed set of feedstock resources. So there are 7 basic subsystems on a board of spacecraft, interstellar spacecraft as well. We have a propulsion system, we have attitude and orbit, and so on and so forth, thermal control, etc. Now, what I submit is that there are only, you could actually store a feedstock of just 10 basic materials to supply the full functionality of the spacecraft for a general robotic spacecraft. And what we would do is we'd use this feedstock to manufacture whatever device we need to replace, including itself. So it's important that we wrap into this manufacturing facility the ability to replace parts of that facility as well. So just to try and convince you how this might be possible, let's look at Illumina. Now, Illumina itself has properties second only to diamond. It's refractory, chemically inert, it's high hardness. It can be used for tooling, such as drilling. It can be an additive to composites. For example, Cermet is basically a composite of alumina in a nickel binder, and it giving high strength and high temperature tolerance. We can then reduce that alumina directly to near pure metal using molten salt electrolysis. And aluminium itself is a multifunctional metal. It's very versatile. It's a good thermal conductor. It can be used as a thermal radiator, electrical conductor, and so on. And in fact, pylon-mounted electrical cables are actually made out of aluminium and not copper. And of course, as a structural material itself. In addition, we have aluminium powder combusted with iron oxide can actually be used as a weld. And in addition, as well, alloyed with silicon, silumin is actually a wear-resistant material which can be employed for tooling. This is the Demandite, and if you look on the left-hand column, you see the functionality required of a specific material. So these essentially, the breakdowns here are for a typical spacecraft. Typical dry spacecraft, should I say, not including the fuel or the propulsion system. So here we see there are various types of functions required to build a spacecraft here. So let's look at one. Let's look at this one here. This is active electronics. So assuming we're going a little bit steampunk here, as I mentioned earlier, that if we're looking at vacuum tubes, we require actually a handful of materials to build this. So we need Covar for high temperature conduction. We need nickel for the electrodes, tungsten for the cathode, fused silicon glass for some kind of sort of protection. And in fact, one thing I've missed there is the coatings, and this could be things like calcium oxide and alumina itself. So let's look at the manufacturing and converting the feedstock into parts and components. There are many different ways of different types of manufacturing machines we can use for building objects. I'm not going to go into the list there, other than to mention things like milling, laser cutting, and this concept here on the right-hand side. This is actually a micro fab lab, which includes a milling station, some kind of robotic arm, a press, and a manipulator hand. So essentially, we can build relatively small manufacturing machines, but obviously the scale at which they can operate is only actually very small components, but we could have a larger one as well. There are also joining operations. We're going to need things like some kind of welding and wire winding and so on and so forth. But essentially all these processes potentially can be integrated into a Cartesian robotic configuration, some kind of CNC machine type of architecture. Unfortunately, subtractive manufacturing methods waste about 90% of the material, and this is not something we want. So additive manufacturing, which builds parts layer by layer, basically minimize the amount of wastage of material. Now, 3D printing is a very versatile method of constructing 3D structures. There are many 3D printing technologies. I'm not going to talk about them now. But as a roboticist, I tend to view all 3D printers essentially as Cartesian robots. So I'll just mention a couple of things. Electron beam additive manufacturing is essentially an electron gun, a high voltage vacuum tube. It is limited to metals. We're currently working with NRC here in Montreal to use their wire-fed EBAM to look at potential aluminium alloys, again with the view of trying to minimize the number of components we require in those alloys. Now, in addition, the FFC process, which I mentioned very briefly, which is a general technique for reducing oxides into pure metal, yields a sintered metal product. It doesn't actually melt the metal. And this sintered metal powder can be crushed and then 3D printed directly. And this has been shown by a company called Metallisis in the UK. One of the areas we're interested in is actually trying to use solar energy or some kind of illumination energy to power 3D printers. We're looking at multi-material 3D printers. This is our Fresnel lens here. It's a 2 meter by 2 meter Fresnel lens. That will create about 1800 degrees centigrade, so don't put your foot under it. It's not going to be very pleasant. We've actually shown that we can melt aluminium directly onto silicone plastic. Now, it's important to state that this is silicone plastic. Silicone plastic has a much higher temperature tolerance than typical hydrocarbon plastics. So this introduces the possibility that in a single machine, we could actually 3D print multiple materials, plastics and metals. So one of the problems we've had is coupling the energy, the thermal energy from the Fresnel lens into a fiber optic cable. We've been using fairly cheap ones. We need to use some more expensive ones which can transmit in infrared. But that's something we're working on. So the next stage would then to be, once we've had these two heads on this 3D printer, as you can see here, this is our custom 3D printer. Once we've mounted our two heads, one would be some kind of extruder, some kind of silicone plastic extruder. The second one would be a Fresnel lens for basically melting aluminium in a powder bed. It would then be to add some kind of milling head to allow us to shape it more effectively than 3D printing is currently capable of. The final process that we're interested in looking at is 3D printing in silicone plastic, flash heating it in oxygen. And again, we haven't demonstrated this yet, but flash heating in oxygen to drive off the carbon dioxide, and that should leave a layer of silica. And then silica, on top of silica, we can then basically deposit steels. So this should extend the range of metals we can deal with in a single printer. Many of you may be familiar with the RepRap 3D printer. It's a fused deposition modeling 3D printer. It prints plastic, and it's actually on the right-hand side here. If you look at the white parts, they were printed by its daddy. So RepRap means replicating rapid prototyper, and it's a step towards some kind of self-replicating system. If we do want to extend this into a fully self-replicating system, we would have to be able to manufacture the bars, which are made out of metal. Well, there are several ways you can do that. You can use EBAM, we can use selective laser sintering or melting. But the most difficult parts to print would be the electric motor drives, the electronics boards, and the computer hardware and software. So this introduces the concept of the universal constructor. This was first developed by John von Neumann in the 1950s as a model of self-replication. The universal constructor, this picture here is from a NASA study in 1980, I think it was, or maybe 1979. As you can see here, this is basically a kinematic machine, a robot, which basically picks parts out of a store of prefabricated parts and assembles copies of itself. So, but it can also potentially manufacture any machine. So depending on what's in this storehouse here, it can reconfigure itself into a different shape or whatever. So that's what the essence of a universal constructor is from an engineering perspective. Frank Tipler talked about it from a different perspective a couple of days ago. If we want to adapt this universal constructor to an unstructured environment, we need to use a suite of kinematic machines. And one of the things one of the hypotheses I have is that all machines of production are kinematic machines, from milling stations to manipulators to vehicles and so on and so forth. And one of the machines of production is the 3D printer suite. Now, the 3D if we relax the idea of what the 3D printer is, not a single machine but a series of machines, potentially this can constitute a universal constructor. Now, any kinematic machine is basically a kinematic configuration of electric motor systems. And so if we can show we can 3D print electric motors, sensors, and control electronics, then essentially all else follows. It means we can manufacture, using 3D printers, other manufacturing machines. So one of the things we've been doing is trying to 3D print an electric motor, and we've been successful. So this electric, do you want to try and run that? Great, fantastic, thank you. So this is a 3D printed electric motor that we printed a few years ago, actually just before COVID. It's comprised of a material called protoplaster, which is basically a PLA polymer embedded with iron filings. We actually got the 3D printed permanent magnets from Oak Ridge, who were kind enough to supply us with their 3D printed magnets. The wiring was probably the most challenging part, and we used a technique called laminated object manufacturing to basically 3D print our copper tape and commutator. The complexity of winding it around the motor in a transverse sense made it quite. We basically printed components. We printed each component, but we had to assemble it by hand. We haven't actually managed so far to automate that process into some kind of robotic assembly. The shaft and bearings were also 3D printed. So if we can 3D print motors and other parts of the motor system, then I would suggest that if we employ this as our main manufacturing facility on board a Starship, we can 3D print pretty much any type of machine that we need to fix anything. And I would suggest that if we can do that, if this becomes standard in a Starship, I'd suggest it's actually a relatively small step towards a fully self-replicating spacecraft, Starship. So this is where we're at. This is actually something I've been working on for a few years. This is a lunar industrial architecture. It comprises, we basically pick up a lunar regolith and we then process it, crunch it, and do whatever else we need. And then we basically chemical process it and then 3D print it into various components here. So what we're doing here on board the Starship is this, drawing a line along here. So we're doing this part, and a full industrial architecture, i.e. a self-replicating machine, requires this part as well. So we're already partway there towards a self-replicating Starship. Yep. Oh. Ooh. Thank you. Yeah, the dividing line is here. Okay. Thank you. So in order to control our industrial activity on board the Starship, we're going to need a fair amount of AI type of capability. So what I want to do now is to quickly run through various approaches to artificial intelligence. The current ascendant approach is based on artificial neural networks. Now, it's unfortunate in many respects that neural networks are called neural networks because it adds a layer of mysticism to what the neural network is doing. It's actually very simple. There's something called the Stone-Weierstrass theorem, which states that the multi-layer perceptron, which is a type of neural network, can approximate any nonlinear function. So what this is saying is all that the neural network is it's a mapping system which basically approximate a multi-dimensional curve-fitting algorithm, similar to a polynomial function, but in multi-dimensional space. And so by presenting input and output data, it's trying to find that curve fit to match those data sets. The multi-layer perceptron requires a minimum of 3 layers. You have an input layer, an output layer, and in between a hidden layer. And it's the hidden layer is the key, which provides the nonlinear mapping capability. This is the output to the neuron. It's basically a summing amplifier in here. So I've actually shown it in a circuit form. So this is basically a summing amplifier here. This is this first part. And we actually have a bias as well, which mathematically you incorporate into the weighting system here. And we have something called a squashing function, which essentially limits the range of the output and imposes this nonlinear behavior. And again, we've implemented that here, the squashing function here. So if the sum of weights exceeds a certain value, the bias value, the neuron fires, otherwise not. And then we put all these together into a network, and hey presto, we have our mapping function. Now, there are various different ways of, there are very different types of squashing functions. There's the sigmoidal function, which is fairly typical, but there are other ones like the signum function, which is used in the original Markov-Pitts neuron, which gives a discrete output for modeling logic gates. And there are also Gaussian functions as well. But the neural net is not a mysterious entity. It's a pattern recognition machine. Now, and again, what helps to mystify it is that the neural net is actually opaque to analysis because the information is spread through its weights, its weight distribution. It's not possible to analyze it in any sort of like any logical in any logical way. We train a neural net using various techniques. The most common technique is called the multi-layer perceptron backpropagation algorithm. And again, there's nothing mysterious about this. It's simply a steepest descent algorithm. It basically in the phase space of the weights and how they change with the error, it basically follows this pathway to minimize the error resultant from the shape of this phase space. Can I have this video, please? That one on the right there. Thank you. Great, thank you. Okay, so there are other types of approaches to learning rules. A Kalman filter, for example, can be used as a learning rule, which is a well-known state estimator. The backpropagation algorithm is in fact a degenerate form of Kalman filter, and I've shown it here. One of the advantages of the Kalman filter as opposed to the backpropagation algorithm is it gives you an adaptive learning capability. The learning rate in the backpropagation algorithm is a free parameter, and you just change it by hand. In the Kalman filter, it's basically it's changed according to the statistics of the state estimation process. So on the right hand side here, we have actually implemented the backpropagation in circuitry. We weren't too sure this was possible because most neural networks are actually software and they're algorithms. But we managed to implement this entire algorithm here, this steepest descent algorithm, actually in circuitry, and that video showed you on a rover. We basically trained it using the circuit-based backpropagation algorithm to stop in front of an obstacle. Very simple, but nevertheless, it demonstrates the possibility we can build learning algorithms in hardware. Do you want to get that pointer back? Okay. There are other types of learning. I'm sure many of you come across the concept of reinforcement learning. I don't want to go into too much detail. In the paper that I've submitted, there's a lot of detail, a lot of technical detail about all this stuff. So I'm just going to skim over it. Reinforcement learning is very similar to what's commonly known as classical conditioning. I'm sure if I mention Pavlov's dogs, everybody knows what I'm talking about. Reinforcement learning is a variation on classical conditioning. There are some more modern techniques. The Rescorla-Wagner model of classical conditioning has now been supplanted by some more sophisticated reinforcement learning algorithms, such as temporal difference, and the Q-learning algorithm is probably the most commonly one. And in fact, reinforcement learning of deep networks was actually during the process of self-play was the basis of the AlphaGo Zero algorithm. I'll just briefly mention deep learning algorithms because it's all the talk of town. Basically, it's many layered rather than three or four for the backpropagator for the multi-layer perceptron. It basically requires quite a large number of layers of neural networks. Typically, the front end is what is known as unsupervised, and the back end is typically supervised, and it's trained in a particular protocol. And an example is the convolutional neural network, which has been used for image processing. There are other ones as well. Now, if you look at the convolutional neural network, there's been no significant improvement in its performance over the past 25 years. And yet it can't do what humans can do quite easily. The CNN requires an enormous training data sets, and yet at the same time makes some really fundamental errors under odd circumstances. And yet a human can learn patterns within just a few images. Another thing about these large networks, biology has shown us that you don't have to have a large neural network in order to function adequately in the real world. And if we look at the worm, it possesses only a few hundred neurons, yet is capable of adaptive behavior. So this, to me, is an indication that we're barking up the wrong tree in many respects. I'll only briefly mention recurrent neural networks. ChatGPT is an extension of a recurrent neural network. The original motivation for recurrent neural networks was to predict word sequences in language. And ChatGPT does this, though it uses a different approach. ChatGPT is a transformer neural network, which is a recurrent neural network that can process essentially whole sentences rather than word by word. And of course, it has enormous data sets. And again, I'll show you why I think that's probably a bit of a dead end. So yes, these large language models, they're based on the transformer network, and they're statistical models of the relationships between words. So they model the probability of adjacent words, and the larger that context, the more accurate that prediction can be. So we're familiar with ChatGPT. I personally think that you can tell quite easily if a student is giving you something written by ChatGPT, because you can see it's a random meander. That's by the by. So if we look at the computational resources required to train these, GPT-3 was a neural net that comprised 175 billion parameters. That means weights or associated weights. And this is close to the approximating number of neurons in the human brain. A common argument in the olden days, not so long ago, was that we will develop artificial intelligence when we figured out how to scale them up to large capabilities. And I think this has shown that that's not the case. We haven't been able to demonstrate human-level intelligence by scaling up neural networks in this fashion. The latest, the MTNLG network has 530 billion parameters, and yet only offers a marginal increase in performance against various benchmarks compared to GPT-3. So look at the energy required. GPT was trained with 1.3 gigawatt hours of electrical energy, which is a huge amount of energy. GPT-4 was trained using 25 to 30 gigawatt hours. So there's going to be a limit to which we can how large we can make these transformer networks. So I think GPT shows us the limit. I mean, there was a program called ELIZA, which was a similar type of it was basically a text processing algorithm that generated plausible responses to queries, and yet people anthropomorphized what was going on in the actual AI system. And I think this is more a reflection on the gullibility of human beings rather than anything to do with what these AI systems can do. I mean, for example, I asked how much energy is required. I'm interested in solar power satellites, so I was interested in looking at something called the energy return investment. So if we're to launch solar power satellites into space, we get a certain amount of energy output over a period of years back again. So what's the energy required to input to manufacture the propellant? And I asked that question, and it didn't even understand the question, because it went on about launchers, liquid hydrogen, liquid oxygen, et cetera, et cetera. But it has no understanding of reality. And for me, this got to be a dead end for AI. And I think the key is we have to understand motor learning. I'm a roboticist, so I'm biased, but I'm right. The key is we have to understand how to embed AI into the real world, and it has to be trained much like a child. I'm told that how long have I got?
We're kind of over on time.
Okay, right. I'll just do one thing. We started looking at this. We wanted to demonstrate transfer learning from one motor environment to another motor environment. So when we learn our motor skills, we learn as babies. You prod a baby and it goes like that. And what it's doing is actually trying to learn a model of its body, how to control its muscles, and that gets stored in the cerebellum. And we wanted to emulate this. So we trained a robotic system on Earth to perform some fairly simple maneuvers, essentially modeling the human cerebellum. When we tried to translate that into a space environment where the dynamics are slightly different, but the form of the equations are identical, it couldn't learn it because it's based on input data sets. And so what was being learned in the neural net was a primitive, it was not rich enough as a model of what we trained it to. It was not rich enough to incorporate the dynamics of the real system. So when we translated that into space, it just we had to train it from scratch. And yet a human astronaut gets, a little bit of training underwater, and they go up to space, and they're quite happy to move around in 0G. And so to me, just to cut this bit short, all the details are in the paper, but the conclusion I have is that we don't understand what human intelligence is. We don't understand how the brain works. We don't understand how to make something truly artificial and embedded in the real world. And until we do, AI will never be up to scratch. That's it. Thank you.